Hello, good morning, and welcome to CS422 Theory of Computation. And today we're going to start with a new chapter 3 on computational complexity theory. So let me start the slides. And the slides are here. Chapter 3, computational complexity. And you see the overview. We will first modify our formalization of an algorithm, which used to be while programs. And now we're going to introduce while plus programs, because while plus programs are given more realistic conception of computational bit cost. So for computability purposes, while programs are appropriate, as are while plus programs. But for complexity investigations, while programs are not suitable, but while plus programs will turn out to be the right notion to capture computational complexity. And after that, based on that, we're going to investigate the complexity of some integer arithmetic operations, and in particular of the pairing function, which we have used so often, which we've already established to be computable, and its inverse. And now we want to know how costly is that pairing function that we've used all the time, so that in the future, the subsequent investigations, we can also build on that for complexity investigations of more complicated problems. Then we will recall some arguably major complexity classes: P, polynomial time decidable; NP, from the P versus NP millennium problem; P space; and exponential time. And there are many more. There's an entire complexity theory zoo, and some of them will be treated in chapter 4 on advanced complexity. But for now, we're going to suffice with these 4 classes and their relations. It turns out that they form a hierarchy. In order to talk about computational complexity of problems which do not involve integers and therefore are not cannot be covered by while or while plus programs, we need to discuss how to encode these problems. In computability part, chapter 1 and 2, this was not really relevant. And here it's also not entirely, not really subtle, but we need to address the elephant and talk about how to encode non-integer data as integers, because then we can start look at some example problems: 3-colorability, Eulerian cycle problem, Hamilton cycle problem, vertex cover, edge cover, integer linear programming, independent set, and click. These will be example decision problems that we consider here and try to classify into these complexity classes that we've introduced here before. And then we're going to give an alternative characterization of the class NP, namely in terms of non-deterministic while plus programs, which is a variant of the deterministic while plus programs we'll have introduced here. And this is similar to the duality between the semantic and the syntactic arithmetic hierarchy. So what we're going to do here is we first introduce a syntactical definition of NP, and then using the non-deterministic while plus programs, a semantic definition, and prove both to be equivalent. So that's our plan for chapter 3. So let's buckle up and start with introducing while plus programs. And to motivate, let us recall the ordinary while programs that we've used through the computability parts, chapter 1 and 2, with these operations, two kinds of loop. And in particular, let me emphasize that here we can increment and decrement as long as the numbers remain non-negative. But the disadvantage of these while programs is that, for example, adding, remember we proved that one can express addition in terms of these while programs by repeatedly incrementing, but this is very slow, right? If you want to add 1 million to some variable, that means there's going to be a loop repeated 1 million times, which not only seems but is unreasonably inefficient, but there's no way around that using while programs. So while program to add two n-bit integers, as we've introduced in chapter 1 and 2, takes an exponential number of steps, and exponential here means exponential not with respect to the value that we want to add, not with respect to 1 million, because the loop is just executed 1 million times. There's actually linear in the value that we want to add. But in computational complexity theory, one is always interested in the computational cost depending on the binary length, which is encoding in binary. And here a number like 1 million can be has a binary encoding which is roughly 20 bits. So in term depends on this 20 bits binary length, having a loop repeated 1 million times, that's exponential. And in general, let me take that opportunity to emphasize and to clarify, because that's a common source of confusion between binary length and value. So the difference is basically between exponential and logarithmic. So imagine a binary integer of n-bit length. In the worst case, this means these are n bits all ones, so that the value is roughly 2 to the n minus 1, 2 to the n plus 1 minus 1, which is exponential in the binary length, and vice versa. The binary length is logarithmic in the value. Recall that duality between logarithmic and exponential. One is the inverse of the other. So in order to perform, analyze computational cost depending on the binary length or on the value, will in general have an exponential difference. And for example, consider the integer factorization problem. The naive algorithm like sieve of Eratosthenes, or even simply trying all possible divisors, takes a linear number of iterations, linear in the value of the integer that we want to factor. But for example, in RSA cryptography, the integers to be factored usually have 1,000, 2,000, or 4,000 bits length. So the value is 2 to the 1,000, 2 to the 2,000, or 2 to the 4,000. And here, an algorithm that runs in time linear in 2 to the 1,000 is completely unrealistic. Whereas if somebody came up with an algorithm that runs in time polynomial in the binary length, which is 1,000 or 2,000, polynomial in 1,000, that is very feasible. So this is kind of a warning to be careful not to confuse computational complexity and cost independence on the value with independence on the binary length. So addition in this setting takes integer addition takes an exponential number of steps, exponentially in the binary length, linear in the value. This is unrealistic because this is not how your computer adds n-bit integers, not by repeated incrementing. This is not how you add integers on paper. You add integers digit by digit, and this is called long addition. And this is currently not feasible in while programs, and that's why we instead introduce while purse programs, which do have an additional operation, not just increment and decrement, but instead also add and subtract, as you see here. That's a new primitive, replacement primitive. We can express increment and decrement by initializing a variable with 1 and then adding and subtracting. So that while plus programs in this sense now can perform integer addition in only one step, constant, okay? And this turns out to be polynomial at time equivalent to the Turing machine model, which in this course we deliberately want to avoid for pedagogical purposes. And so this is going to be while plus programs. There's another new operation that I need to address, namely that's division by 2 with rounding down if the original integer is odd. And this is also an operation that cannot be performed efficiently using while programs, but now using while plus programs, it can be done in constant time. But for those of you who are already maybe familiar with Turing machine models, the Turing machine cannot add 2 integers in constant time, but in time linear in the binary length, so that the computational cost in while plus programs does differ from that in Turing machines, but it differs only subtly, only little, namely only up to polynomial, what runs in while plus programs in polynomial time will run on a Turing machine in quadratically larger time, and vice versa. What can be executed on a Turing machine can be simulated on a while plus program with at most polynomial slowdown. So up to polynomial time, this model of computation is equivalent to the computational costs of Turing machines. But as I keep arguing for pedagogical reasons, this one is much more elegant, convenient, and easy to understand. So when we talk about while plus programs, let me also recall how you know the semantics here. It's obvious, but how to input and output, and our convention was and remains is that the input is provided in the variable x1, dedicated variable, and the output, the return value, is provided in the dedicated variable x0, both natural numbers. And again, let us now recall how do we process data which is consists of more than one integer, like tuples of integers, or maybe vectors or matrices. And in the chapter 1 and 2, for this purpose, we would use this pairing function from Hilbert's Hotel. And we saw that this pairing function allows to recover the individual components and to recode individual components into one compound natural number computably. But now how about the computational complexity of doing so? And in order to address that, let us introduce some formal notions of computational cost incurred by while plus program. The first one is the binary length. As I said, in computational complexity theory, one measures computational cost independence on the binary length. But here we don't have binary strings for input and output and processing, as opposed to Turing machines. So instead we have natural numbers, but the binary length is simply this expression, the binary logarithm of 1 plus x rounded up. So why that? Does that make sense? Or why do I define the binary length in this way? Let's look at some example. For example, what is the binary length of 0? The binary length of 0 means here x is 0. Here we have 1. The logarithm of 1 is 0. So the binary length of 0 is 0 here. What is the binary length of 1? Binary length of 1 here means we have 1 plus 1 is 2. Logarithm of 2 is 1. So the binary length of 1 is 1, which makes sense, right? What is the binary length of 2? Binary length of 2 means here x is 2, means here we have 3. Logarithm of 3 with base 2 is a little bit larger than 1, right? Between 1 and 2. The value is 3 is between 2 and 4. So rounding up means that the logarithm now becomes 2. Binary length of 2 is 2, which makes sense because 2 in binary is 1, 0, 2 digits. And similarly, binary length of 3 is also 2, 2 digits, 1, 1. Binary length of 4 turns out to be 3, and so on, so that this is a reasonable definition of binary length. It coincides with what you would consider binary length when writing the natural number x in binary on your paper. Next, let's talk about the running time of a while plus program P on some input, and we consider here for generality both k tuples, that's the initial configuration. So usually all variables are initialized with 0 except for the input, but we also consider later stopping a while plus program at some point and then resuming it where the variables at this point may have non-zero values. And we count the number of steps made by this while plus program, the number of operations, and this is going to be the running time. And as I said, that gives a slight difference to the Turing machine model, because a while plus program can add 2 integers in one step, whereas a Turing machine needs a linear number of steps for that. But up to polynomial time, which we're going to formalize on the next slide, it's going to be equivalent. The next notion of computational cost, of algorithmic cost, is memory, running time and memory. And the technical term for memory is space, for historical reasons. And space of the memory used by a while plus program at one instant in time when the variables, k variables, have some certain values, is we define this to be the binary length of the variables added. Okay, so first variable requires some number of bits to store intuitively, and this number of bits is captured by this expression. Second variable requires a number of bits, and so on up to the last, the kth variable. There are only finitely many variables. Add this number of bits, and this we define to be the total amount of memory currently used. So again, the question arises, is that a reasonable notion? For now, it seems reasonable, but let's compare this. For example, we recall that using the pairing function, we could combine all these variables into one single variable and perhaps save memory, right? Instead of having k variables with different values, we could just have 1 or 2 variables. 2 counter machines are complete. We could introduce this, combine all these variables into one variable and maybe thus save memory, arrive at a different notion of memory use. And to compare the two, let us recall the one explicit expression for the pairing function of 2 natural numbers here. And this pairing function has the property that the binary length of combining a vector, indicated here with this underscore, that is a tuple of natural numbers. So the binary length of this one single natural number is bounded by almost at most linearly longer than having the individual natural numbers encoded in this sense separately, and vice versa, having the individual natural numbers encoded jointly is at most linearly longer than having all numbers first combined into one single natural number and then considering the binary length of the latter. So that up to actually a linear constant factor, linearly both are equivalent. And this is justification that actually in the sequel, we will not distinguish and we will move freely back and forth between having several natural numbers encoded into a single one or kept separately, because at least from the perspective of computational memory of space, it's going to make a difference only up to a linear factor, which we're going to ignore asymptotically. So that's about memory at one instant. But what is the running time and memory consumption when executing a program? We've already defined running time when executing a program, the number of steps. But for memory, we consider the worst memory consumption at any of these number of steps. So maybe at some point there will be a large amount of memory used, and later there may be less memory used. And we consider kind of the worst case, the largest amount of memory used throughout the execution of this program. And here's our first important observation about the memory consumption. How can this change throughout the execution of a wild-plus program? How can this change throughout the computation? And the observation here is that each step may or may not increase the amount of memory, right? For example, dividing by 2 decreases the amount of memory. Actually, it decreases by 1 bit, right? So imagine division by 2 is basically shifting by 1 bit, and therefore the binary length decreases by 1. Similarly, subtracting may decrease the value of the variable, right? Remember, we only have non-negative numbers, so subtraction really decreases in general, which also results in a saving of memory according to this definition, right? But addition is what can increase the memory consumption because it can result in larger values as previously according to this definition. But the important observation is here that addition can at most double the value currently stored. So consider, for example, the largest value stored in any of the variables at some point. And if the program adds these 2 values, that means basically doubling the value. And doubling the value means increasing the binary length by 1, right? Doubling meaning shifting into the to the left, meaning increasing the binary length by 1. And this is the worst that can happen in one step, right? All other operations either do not change the value or decrease the value. And the worst that can happen in one step of increasing the value is doubling and thus increasing the binary length by 1. So in the worst case, each step can only increase the memory consumption by at most 1 bit. That's important to keep in mind because, for example, it means that any program, wild-plus program running in polynomial time, making at most a polynomial number of steps, will also only have a polynomial amount of memory, polynomially more than the initial data, which also uses some memory, but we're not going to charge for that. So important consequence of this observation is that any while plus program that runs in polynomial time will also use at most a polynomial amount of memory, a polynomial number of bits. And now I've already talked about asymptotic running time and asymptotic memory consumption. And we use the symbols T and S for the two, T of n and S of n, S for space. And these denote the worst case. Again, the second time worst case. Here we had a worst case, but this time the worst case is over all inputs. Here the worst case was over the course of the computation. At each instant in time, investigate how much memory is used, and then take the largest amount of memory used throughout the computation on one specific initial input. And asymptotically means we now also let the inputs vary, and we let them vary over all possible inputs of length, binary length, less than n. So that means inputs can have values up to 2 to the n minus 1. And this is in correspondence with the Turing machine model, where also one considers as n a bound on the input length, the binary input length. So this, now we have introduced the notions of computational cost. We had our first observation about the relation between polynomial time and polynomial amount of memory here. And now I'm going to have a short break here. A short break in order to answer two great questions from the chat. The first question is about the semantics of subtraction. And indeed, the question asks, for example, what if we subtract 3 from 2? What is 2 minus 3? Taking into account that our while programs only can deal with non-negative integers, with natural numbers. And indeed, as with while programs, when we decrement 0, the result would remain to be 0. And similarly, if we subtract 3 from 2, the result will be 0, not minus 1 or anything negative. So it's kind of below, everything is cut off below 0 to be exactly 0. Thank you. Great question. Well justified. Thank you for letting me clarify that. And the second question is about input and output of tuples. And as emphasized, yes, for computability purposes, we the pairing function would allow to combine several natural numbers into one and back computably, so that for computability purposes, it makes no difference if we only could allow for one single input and one single output, or if we allow for several inputs and several outputs, with or without forcing these several to be first or later encoded into and decoded into one single one using the pairing function for computability purposes. But the question indeed remains now open. How about when we now talk about complexity? We already saw that for space consumption for memory, it makes at most a linear amount of difference, right? But how about the running time difference? That's a question in the chat, and this is so great a question because it actually leads to the next slide where exactly this question is addressed. So in the next slide, we talk about the computational complexity of some arithmetic operations on natural numbers when expressed in while plus programs. And first step is about multiplication of integers. Now that we had addition we don't need to express addition by repeated incrementing or subtraction by repeated decrement. We can do addition and subtraction in one step each. But how about multiplication? Again, we had this trivial algorithm when we discussed computability, which would express multiplication by repeated addition. But this now would result again in exponential time algorithm, exponential in the binary length, linear number of addition, repeatedly addition, linear in the value that we want to multiply, but exponentially in the binary length of the value that we want to multiply. So this is again unrealistic, but fortunately, we don't need to change the model another time. There's no need to introduce a new further model while plus times program, because we can also express multiplication using while plus programs using only a linear number of additions. And this method is what you used in high school, what you're well familiar with. Namely, it's I think it's called long multiplication, where you kind of write the shifted, repeat the first argument with the shifted positions, and then you add the shifted positions. And now recall that shifting means multiplying by 2, and multiplication by 2 can be expressed using addition with itself. So that long multiplication can be expressed in while plus program, and maybe that's a nice exercise for you to write a program, while plus program, realizing a long multiplication with a loop which is linear in the number of steps. And also there's some attention to be paid. How often will the program execute the loop? How will the program know how often to execute the loop? So I think that's a great assignment exercise. So now we've covered long multiplication, and again, let me emphasize that this is a little different from the Turing machine model, where the best known algorithm for integer multiplication due to Martin Führer takes a number of steps which is n log n, so up to logarithmic factor of difference here. In general, polynomial difference at most between while plus program and Turing machine model. But as we're going to discuss polynomial time complexity, that is not really a big issue here. Good, so now we've covered arithmetic, addition and multiplication in linear time, division, long division with remainder, right? You see here it's only division by 2 is supported. Division by other numbers, division with remainder can also be expressed in a linear number of steps, and I leave it to you to implement that. But we're heading at the original question from the chat. How about encoding and decoding pairing function? And yes, to this end, observe that the pairing function is basically arithmetic, right? So there's some additions, there's a multiplication, and there's a division by 2, which is guaranteed to not incur any rounding, because precisely one of these two numbers is even anyway. So that means altogether, one can express the pairing function again in linear time using this long multiplication here, and a little bit more subtly also the unpairing function. So given a coded pair, recovering X or recovering Y or recovering both can also be done in a number of steps, which is linear in the binary length. But this is a little bit more subtle. It requires some binary search for the trying values X and Y. And again, I'm going to not go into detail here because it's not the focus of this lecture in computational complexity. We're more interested in polynomial time or not, P versus NP. So let's go there and introduce some major complexity classes. And to this end, let us first recall and refine the notion of computational complexity of a function. Remember, we defined the that an algorithm informally first is said to compute the total function if on input x, it eventually prints f of x and then terminates. Termination is important to avoid prevent the algorithm from reverting its purportedly first output. And as the next steps, we formalized algorithm to mean while program. And now we have just proceeded in formalizing while program to instead a while plus program. So computing a function means that for a while plus program to compute the function in time t of n means that the computation makes at most t of n steps where n means the binary length of the input. And similarly, computing such a function in space, in memory S of n, means that at all instances for all inputs of binary length up to n, and throughout all computational stages, the computation will incur at most S of n memory binary length of all temporary variables combined. So that's our definition of computational cost. And analyzing computational cost exactly is maybe involved in tedious and distracting, because we're more interested in the general asymptotic behavior of running time and running space, and even more costly, only the question whether it's polynomial or not. So it can make a huge difference between a linear time or quadratic time or cubic time algorithm. But first we want to see whether there's a polynomial time algorithm or not. And only once we have found a polynomial time algorithm, then one can and should indeed look more closely whether what is the degree of this polynomial. So let us here first focus on the question polynomial or not. And major difference is exponential time algorithm, which we define not only to mean 2 to the n or 4 to the n or some constant to the n, but 2 to the polynomial in n, which is more general, which is more generous. But the reason, the benefit will turn out to be some closure properties. And speaking about closure properties, why is polynomial time such a important complexity class? And for example, quadratic time is not a popular complexity class, although quadratic time algorithms are indeed very important and desirable in many cases. And the reason is closure properties. Quadratic time algorithms are not closed under composition. I mean, just intuitively, if you have two quadratic time algorithms and you combine them, the result may in general be a quartic time algorithm, right? So not a quadratic time anymore. The quadratic time algorithms are not closed under composition, but the polynomial time algorithms are closed under composition. And let's look into that here and make two observations. First, that polynomials are closed under composition. If you take two polynomials, univariate polynomials and form their composition, then the result will again be a polynomial of higher degree, all right, but still it will be a polynomial and in particular not exponential. And the second observation is why the reason why I emphasize here this S compositions is that if F and G are both polynomial time computable, then also the composition G after F is polynomial time computable. And this is not immediately obvious, so let me argue why this is the case. It builds on the aforementioned observation that in each step, the binary length can at most increase by 1. So if we consider polynomial time computable function f, then it means that an input of binary length n can be transformed into an after t steps into an intermediate configuration of binary length at most n plus t, right? Proved by induction. In each step, the memory consumption binary length can increase by at most 1. So after t steps, the binary length can have increased by at most t from the original binary length n. And after termination, which is guaranteed by hypothesis to run in polynomial time, the binary length may have increased by at most polynomially, so that the output of the function f will have binary length at most polynomially in the binary length n of the input. Let me say that again. Polynomial time computable function may result in the output be longer in binary than the input, but at most polynomially longer, which follows from induction of our previous observation that a while plus program can increase the memory consumption, that is the binary length of all variables, at most 1 in each step. So after polynomial number of steps, it can have increased at most polynomially. And that's important because once we now invoke the second while plus program computing G, again promise to do so in polynomial time, that means that now the computation running time for G is polynomial in the binary length of the input to G, which is not necessarily the same as the original input to F, but it's the output of computing F. And as we've just argued, the output of computing F will be at most polynomially longer than the input of F. And then feeding that into the computation of G, which again has a running time polynomial in the binary length of the input of G, will result in other polynomial growth in running time. But as we just recorded, this second polynomial, this one for G, and this one for the running time of F, will again be a polynomial, so that the composition of G of F, the composition of the algorithm computing G with the algorithm computing F, algorithm here meaning while plus programs, will again run in polynomial time, possibly a larger degree, but still a polynomial. So that this is a second kind of closure under composition, which is not satisfied by, for example, quadratic time algorithm, nor is it satisfied by exponential time algorithm, because composing an exponential with an exponential in general can result in a tower of exponential of height 2, doubly exponential. Also, let me emphasize that this is not a duality, that there are algorithms and running times that lie strictly between polynomial and exponential. But for the purpose of chapter 3, it's sufficient to focus on this antipodes polynomial versus exponential time. Okay, so this is actually formalization of what is called Edmonds' thesis. Edmonds had postulated that polynomial time is a suitable mathematical formalization of efficiently in practice. And now we can put Edmond's thesis into complexity classes for decision problems. So in the first half of this slide, we've been focusing on function computation, functions from natural numbers to natural numbers. And now we're going to restrict to decision problems, which we can identify with function problems, where the range is just 0 and 1, namely the characteristic function of the decision problem. And but we will later return to function problems when we talk about polynomial time reduction. However, the famous complexity classes are defined for decision problems. So let's look at them. And the first is the complexity class P of all problems that are decidable in polynomial time. And let me spell out what that means first. In this setting, as opposed to the Turing setting, we're considering decision problems as subsets of natural numbers, not of binary strings, because that's what the while-bus programs can process. And when we mean polynomial time, we mean time polynomial in the binary length of the input, which, as you recall, is basically asymptotically roughly the same as the logarithm of x up to some constant and rounding and shifting, but asymptotically the difference between length and value is logarithmic versus exponential. So this is polynomial time, and we're going to look at example problems that can be solved in polynomial time in a few minutes. But let's first move on to another important complexity class, namely P-space. This is a class of problems that can be decided using a polynomial amount of memory. And right, so this is an important complexity class, and let's already start talking about the relation between these two complexity class P and P space. And the relation is, as I emphasized and repeated, in each step increases the memory by at most 1, so that any algorithm runs in polynomial time can increase the memory by at most a polynomial, so that any polynomial time algorithm actually is also a polynomial space algorithm. Or put differently, complexity class P is a subclass of the complexity class P space. Any decision problem decidable in polynomial time is also decidable in polynomial space. So these are two important complexity class. Now we get to the next one, exponential time. This is problems that are decidable in exponential time, in this sense indicated here. And our next observation is that the complexity class P is contained in the complexity class X. Any problem that can be solved in a polynomial amount of memory can also be solved in an exponential amount of time. And let me spell that out here. Any decision problem that can be solved in a polynomial amount of memory can also be solved in exponential time. And the reason for that is, again, a subtle, simple but important observation is that when we have a while-plus program that uses only S bits of memory, then these S bits of memory, each one can be either 0 or 1, right? And therefore, S bits together can have at most 2 to the S different combinations of values. Each one, 2 combinations. S bits means 2 to the S. And then we have be generous here, 2 to the O of S, for reasons that I'm going to explain in just a minute. But the important observation here is so that when S is, for example, polynomial in N, because if we consider a problem in P space and an algorithm, a while-plus program that uses at most S equal polynomial in N amount of memory, then that program will have at most exponentially 2 to the polynomial in n a number of configurations. And here the crucial observation is if 2 of these configurations agree, that means if at some point all the variables have the same values again at the first point of time and maybe an hour later again, and also if the program counter is the same, then the program will just repeat the same calculations as previously. Let me say that again. So the program's execution is uniquely determined by the values, the states of its variables and its program counter, right? So imagine you run a while plus program for an hour, and then you want to, you kind of freeze the while plus program, you store its variables onto some external memory, and you store the program counter, which instruction has just been finished executing. And then later you can resume that while plus program by recovering those 2 information, the values of all variables and the value of the program counter. And then the program will resume exactly in the same way. So that means when during the execution of such a program at some point, the same configuration occurs a second time, the first time at some point and later a second time, then that means that the second time the next operations will also be the same as the first time, and therefore the same configuration will occur a third time again, and then a fourth time, and then on and on and on infinitely often. So that this means if any configuration repeats once, then it will repeat infinitely often, and therefore the program will fail to terminate. Let me say it again, it's important. If during the computation of a while plus program, some configuration gets repeated once, then it will get repeated infinitely often, and therefore the while plus program will fail to terminate, and thus is not a polynomial space algorithm, because a polynomial space algorithm must in particular decide and therefore terminate. That means that every terminating while plus program that uses at most s bits of memory can make at most exponentially many steps, because otherwise it would, by pigeonhole principle, some step would repeat, and thus the program would repeat indefinitely, fail to terminate at all, and thus is not a decision program by contradiction. So any while plus program that does terminate and using at most as polynomial space will use automatically only exponential number of steps. So now we've already established and proven our second inclusion between these complexity classes, but the arguably most famous one is still missing, right? Amy, the one from the Millennium problem, the P versus NP problem. And this is what you see here. NP is the class of decision problems that are verifiable in polynomial time. Verifiable as opposed to decidable. And I'm going to define what it means to be verifiable. And that is going to be what may be called the syntactic definition of NP. And later in this lecture, we're going to give the semantic definition, equivalent semantic definition of NP based on non-deterministic while plus programs, but that's for much later. For now, we define class NP to be all decision problems of this form, and we call them verifiable. The decision problem of this form, it contains all natural numbers to which there exists another natural number y, whose length is at most polynomially in the length of the input. We call this is the input, okay, basically the argument. The second y is called the witness. The length of the witness must be at most polynomial in the length of the argument x, such that the pair x comma y belongs to v. V is short for verifier, and it's required to be polynomial time decidable problem. So we've just defined polynomial time decidable problems, and V, the verifier, must be polynomial time decidable. And now we have defined polynomial time verifiable. And it's called verifiable because given a witness Y to X in L, then it's easy to verify that X indeed belongs to L by verifying that the pair X comma Y belongs to this polynomial time decidable decision problem, the verifier. Why is this an interesting complexity class? We're going to give many examples in the next slides that are easy to see to belong to this class, that are easy put into this form, that are easy to see verifiable in polynomial time, but not easy to see, or not even easy, or not even known to be decidable. So many problems are easily seen verifiable, but not necessarily decidable in polynomial time. So that this is a very large class. And indeed, the question whether it's the same or different from P, that is the P versus NP millennium problem, which can earn you $1 million. Okay, so here it's let me emphasize that again. This is a syntactic definition. It means a decision problem L is or can be formulated, rephrased equivalently in such a form. And this is how we're going to show that some problems belong to NP. We're going to equivalently reformulate the problems into this form, existence of a witness with the two conditions. First, the witness must be at most polynomially long. And secondly, the property of being a witness must be polynomial time decidable, being a witness to X. Okay, and what we want to do at the remaining of this slide is to put the complexity class NP into this hierarchy that we've already established here, namely, and this is the main theorem for this slide. P is a subset of NP, and NP is a subset of P space, so that we have this very nice hierarchy. And the P versus NP millennium problem asks whether this is actually a strict or not a strict inclusion. It's not known. If you can answer this question, then you will become famous. But also equally unknown is whether NP is a proper subset of P space or not. We're going to prove these two inclusions in a minute. And similarly, it's not known whether P space is a subset of exponential time. It is known, and we will prove that later, that P is indeed a proper subset of exponential time. There are decision problems that can be solved in exponential time, but not in polynomial time, provably. So somewhere here in between, there must be a proper inclusion, but which, where, and maybe all of them, that's not known until nowadays. Okay, and I now still owe you the proof of these two inclusions. And for the first inclusion, let us consider this trivial kind of verifier. So let's say we have a decision problem L, which is polynomial time decidable, belongs here. And to show that it belongs to NP, we need to rephrase it equivalently in this form with a witness. And to this end, we just introduce kind of a artificial dummy witness. Namely, we consider as verifier the set of all pairs X comma Y, where X belongs to L. And observe that this is polynomial time decidable because by hypothesis L is polynomial time decidable. So we just take the input and throw away the y from the pairing function, and then invoke the algorithm while plus program, testing whether the rest belongs to L or not, which by hypothesis is possible in polynomial time. And thus means that this verifier is polynomial time decidable. And then we have rephrased L in this form, because now the existence, whether there exists a witness or not, however long it is, it does not change. It only amounts to the question whether X belongs to N, which is a tautology. So this proves the first inclusion. And for the second inclusion, we design an algorithm that runs in polynomial amount of memory that checks whether there exists a witness or not deterministically without verifying. Namely, it tries all possible candidates Y. So let me say it again. Now, the final inclusion of this hierarchy is what we're proving. And the proof considers a problem in NP, which by definition is of this form. And it's not necessarily polynomial time decidable because of this existential quantifier. But we can have an algorithm kind of computationally interpret that existential quantifier by trying all possible candidate witnesses Y. Unfortunately, there are only finitely many because we only consider here witnesses of length up to polynomial in the binary length of the input. That's fortunate, so it is decidable. One can try all of these witnesses, but unfortunately, there are exponentially many witnesses, right? So how many candidate witnesses are there of binary length at most polynomial? 2 to the polynomial, right? Binary length means logarithm of the value. Therefore, the value is at most exponential in the binary length of the input, which means there are exponentially many candidate witnesses. So this is not a polynomial time algorithm, but it's a polynomial time space algorithm. Why is it a polynomial space algorithm? Because checking whether a current candidate witness is indeed a witness can be done in polynomial time by hypothesis, and therefore can be done in polynomial space by the previous inclusion. Anything that can be done in polynomial time also happens only within polynomial space. And when we then consider the next witness, we can reuse the space used by the previous witness without increasing the space, so that the space consumption is really the space consumption of the polynomial time, this time algorithm for this verifier, plus the memory of the witness, which is at most polynomial. And this takes exponentially many witnesses, but it reuses memory so that the overall memory consumption is still polynomial time. And thus we have proven this inclusion. So I guess that's already a lot. That's enough for today. That's enough for the introduction to computational complexity theory. So we've summarized, we've introduced a variant of the while program that we used so far for formalizing computability investigations, for formalizing a notion of an algorithm. And we've modified that to while plus program, which in addition to increment and decrement can also add and subtract numbers in one step, which otherwise would require unrealistically an exponential number of steps. And now it only takes one step. And we've seen that this allows also to express multiplication in polynomials, specifically a linear number of operations. So we don't need to, we can stop here with introducing arithmetic operations. No need to have multiplication as an additional arithmetic primitive. And then we've investigated both the memory consumption and the computer running time of several arithmetic problems, including pairing and deep pairing function, which turned out both to be feasible in polynomial time and in a linear amount of memory. And then finally, we've introduced the famous complexity classes P, NP, as well as P space and X. And we've established that these form this hierarchy, which is not known to be strict or where it is strict or not. And this is actually the millennium problem. So that's all for today. And next time we're going to continue, and we're going to consider example problems and try to put the example problems into these computational complexity classes. Thank you very much for your attention, and see you next time.